Hi, Assalamualaikum and very good morning to Dr. Siti Nurul Ain. My name is Muhammad Firdaus Haziq, and today I would like to present my research project entitled Correlation of Crystallite with Different Thermal Behavior of Nickel Cobaltite Catalyst. So, for the introduction, fossil fuel burning produce massive carbon dioxide emission. New energy resource with low environmental impact should be used to achieve sustainable development, which is a catalytic methane decomposition. Commonly used catalyst supported for catalytic methane decomposition is nickel, ferrum and cobalt. Supported metal show less selectivity and reactivity, so nickel-based unsupported catalyst is an option since its operation limited by deactivation at high temperature. Nickel cobalt catalyst is promising catalyst since it is stable, good electrical conductivity, good catalytic activity and electrochemically active than nickel oxide and cobalt oxide. So we go into problem statement. Currently, traditional heterogeneous supported catalysts show less selectivity and activity. The metal would be divided by charging force, which may it changes their properties. It is very depending on electronic state of metal particles, crystalline size, textural properties, catalyst composition, and preparation method. So we go to order objective. This study have two objectives, which is to synthesize the unsupported nickel cobaltite catalyst using hot fusion method, and second is to analyze the crystalline size of nickel cobaltite with different thermal behavior using DSC and TGA equipment. So we go to the scope of research. First, it is an introduction of unsupported nickel cobaltite catalyst to biomethane decomposition. Second, a different thermal behavior of nickel cobalt catalyst affect the crystallite size and their characterization. And last is a hot fusion preparation method to synthesize the catalyst will affect the catalyst characteristic and properties. So we jump into the methodology. First is a mixing of nickel nitrate hexahydrate, cobalt nitrate hexahydrate and citric acid monohydrate with mortar and pestle for 1 hour. Second, the solution then was fused in the arc furnace with 3 different temperatures, which is at 700, 800 and 900 degrees C for 5 hours. Then the catalyst then was labeled as nickel cobalt 700, nickel cobalt 800 and nickel cobalt 900. The characterization of nickel cobaltite catalyst were done using a thermogravimetric analysis TGA and differential scanning calorimetry DSC. So the TGA analysis were done in thermogravimetric analyzer to assess the oxidation stability, purity and graphitization degree of nanocarbon deposited at 900 degrees C. The weight loss percentage was less significant with the introduction of nickel, indicating the reduction of catalyst water content in the presence of nickel. For result and discussion, it was observed in figure 1A, B and C that there was no thermal degradation in the temperature range of 200 until 350 degrees C, which correspond to the existence of amorphous carbon. For the nickel cobalt catalyst fused at 700, the thermal degradation started at around 620 degrees C. There was a weight loss of 0.013%. For the nickel cobalt catalyst fused at 800, the degradation started at 570 degrees C with an increasing wave up to 0.004%. For the nickel cobalt catalyst fused at 900 degrees C, the thermal degradation initiated at 625 degrees C with a weight loss of 0.013%. The onset temperature for nickel cobalt 700, nickel cobalt 800 and nickel cobalt 900 are 620 to 825 degrees C, 570 to 810 degrees C and 635 to 845 degrees C respectively. The increasing weight of a catalyst sample for the TGA analysis may be because of the existing of the contaminant and impurities oxygen in dry nitrogen purge gas that lead to the absorption of oxygen. Another significant factor which influence the true sample temperature and weight are the effect of radiation on the sample. At above 500 degrees C, the radiation becomes dominant mechanism for heat transfer, particularly when using an open cup sample pan. As example, at the same condition, a black sample can be at temperature higher than white sample. So we go to the figure 2, which is a DSC analysis result. The DSC analysis was done for nickel cobalt 700 only due to the limitation of the DSC crucible pan in laboratory. So basically DSC is a technique in which a sample is measured with heat flux to or from a sample is measured versus time or temperature, while the temperature of the sample is programmed in a controlled atmosphere. So, a large endothermic startup hook can be seen. It is caused by a significant baseline change due to the variations in the heat fluxivity of the sample and the reference crucible. A notable endothermic peak occurs at a temperature range from 50 to 70 degrees C, resulting from evaporation of free water in the catalyst. The fluctuation can be identified on this curve at 150 degrees C and 300 degrees C, which may either result from the volatilization of internal water absorbed in pores inside the catalyst sample of nickel cobalt 700 or the interaction between catalyst sample with gas carrier. So, the weight loss appears at 400 degrees C and 470 degrees C, which is due to the thermal decomposition of nickel cobalt 700. So, for the conclusion, the catalytic stability of nickel cobaltite catalyst was demonstrated for the methane decomposition study. The catalyst was synthesized by mixing the nickel nitrate hexahydrate, cobalt nitrate hexahydrate, and citric acid monohydrate, then fused in the furnace, which is a hot fusion method with temperature up to 700 degrees C until 900 degrees C. So for the TGA analysis, it showed that the nickel cobalt 900 have higher thermal degradation initiate at 625 degrees C. Some error might be occurred by the increasing pattern of all catalyst sample weight either due to the sample oxidation or moisture absorption. So thank you, that's all from me.